So in this session, we'll be discussing about the
Good evening, sir.
Good evening, ma'am. So we'll be discussing about the ensemble learning methods. Okay, so specifically we'll be more focusing on the bagging and boosting concepts. Okay, so before we're going to see the details of this ensemble learning techniques, let us try to understand what is ensemble learning method. What is ensemble? When do you call it as ensemble? When you combine multiple methods, we call it as an ensemble, isn't it? So ensemble is a combination of multiple models. That's what is the ensemble is. When you can combine or integrate multiple models together, we call it as an ensemble learning model or ensemble learning method. So we have a simple ensemble learning techniques like voting or averaging or stacking, right? So in this, let us start with the simple ensemble learning techniques. Like I have shown you here, voting, which is demonstrated or illustrated in the first figure, in which we train the multiple different models using the given training data. So use this training data, train SVM, give it to SVM and get SVM. Train the decision trees using the same training data, or you train some other model using the given training data. So given a new instance, give it to all these individual models, give it to SVM. Let's say it is classifying it as a spam. Give it to decision tree, it is classifying it as a non-spam. Give it to KNN, let us say it is classifying it as a spam. So majority of them are classifying it as a spam. So therefore, assign a label spam to the new instance XN, right? So this we call it as a voting scheme, right? So in which we train multiple different models using the same training data. We train multiple different models using the same training data, and to classify a new instance, we give this new instance to all these individual classifiers that we have trained. And then we take the majority voting. This scheme, we call it as a voting scheme. So if it is a regression problem, you can take the average of the individual outputs, and that is called the averaging scheme. So voting we follow for the classification problem, and averaging we follow for the regression problem. All right. So the next one is stacking. The models are organized at multiple levels in case of stacking. Like for example here, you can give the given training data to the multiple models and train the multiple different models. Let's say they are called the level 1 models. So using the given training data, I train SVM, I train decision tree, I train KNN and so forth. Now, whatever the output that I am getting for these models, I take this as a feature vector and train the next level models. I take this classification as the feature vector. This is one vector now, right? So this as a feature vector and train the level 2 models. So to classify a new instance, I give it to SVM, I give it to decision tree, I give it to KNN, and I will get the corresponding predictions. I use that prediction vector as an input for the next level model, and it gives the final prediction as the spam or not spam. So this is how the stacking works. Okay. So if you look at all these simple ensemble learning techniques that we have discussed so far, voting, averaging or stacking, whatever that it is, what they are doing, they're training multiple different models using the same training data, and somehow they are integrating them to get a solution for this or to get a prediction for the new instance, right? So have you got the idea of all these simple ensemble learning techniques? Is it clear?
Sir, what is the
Okay, please go ahead, madam. Please go ahead, madam.
what is the training data we give to the level 2 model, sir?
Training data is this X.
Same
This
question
is
from my
XI,
side.
madam. Yes, yes. This is XI, and the corresponding YI is the original target value.
Okay, sir.
See, we have given x1, y1, x2, y2, so on xn, yn, right? Okay. So we give the input output pairs to the SVM, right? So when you give xi, I am trying to minimize the difference between actual and the predicted values, right? We will get the corresponding yi, model prediction by SVM, right? So now take that as the, I mean, this like this you will get for every model, right? Now this itself is a vector. So take this as xi and take the corresponding yi and train the level 2 model. Got it, madam? Is it clear, sir? Ravi sir? Clear?
Yes, sir. Yes, sir. But the thing is, now which model you consider that it is better, sir? You consider the model, which model is better? How is it work, sir?
We can't say that. We can't say particular model is best.
Okay.
Throughout anywhere, right? If the question comes that which model is best, we can't
Okay.
tell it general. We can generalize. We can't generalize it and say that a particular model is best in all the situations. Okay,
Okay.
depends
You,
on
you
them.
mean to say, you mean to say that when we do like this, the output will be better than using one module? When will we decide, sir, to go for this kind of approach?
Ensemble learning technique. When to go for the ensemble learning technique?
Yes, sir.
Is
Yes,
it?
sir.
Okay, that we
Yes.
will see, sir.
Okay,
Yeah,
sir.
I mean, even if I tell you now, it would be very vague. Okay.
Okay.
So
Okay.
let us complete few models, then you will understand. Otherwise, you please ask me. If you don't get idea, please ask me. I'll answer that.
Okay,
Okay.
sir. Thank you, sir.
Yeah. Fine. But is these two things clear? Simple ensemble learning techniques?
Yes, sir.
Voting average. Yeah.
Are
Give
you
me a
feeling
second.
well, sir?
No, I'm okay. Let me have some water. Please give me 1 minute. Yeah, sorry for that. Yes. So if you see all these models, the commonality between all these models is that they're using the same training data and training the multiple different models. So am I audible? I'm audible, right?
Yes, sir. Perfect.
Yeah. So if you look at all these models, they are training multiple different models using the same training data. Now the question coming in is that instead of training multiple different models using the same training data, can I train same model using the multiple training data? Is the question. So don't confuse. So here we are passing the same training data to the multiple different models. Okay. So now the question is, can I use the different training data and train the same model multiple times? Is the question, right? So from that concept, the concept of the bagging and boosting have been evolved. Okay. So here is the question that which is coming up. Instead of training different models on the same data, train the same model multiple times on the different data sets and combine these different models. Okay. So instead of training different models on the same data, train the same model multiple times on the different data sets. In a sense that, like for example, you see the previous slide, in which we are giving the same training data to the SVM, we are training SVM. Giving to the decision tree, we are training decision tree, and so forth. Right? It means you are training the multiple different models on the same training data. Now, what it is saying is that you take the same model in sense, if you take SVM, take SVM only. So take training data 1, give it to SVM, you will get SVM1. Train it with SVM, you will get SVM1. Now take a different data set T2, training data 2, train the SVM, you will get SVM2. Because the training data is different, you will get different SVMs, right? So like this, you train multiple different models and combine these different models. That's what the idea is, right? So now the another question coming in is that how can I get multiple training data? How can I get multiple training data? Is the question. Have you got this idea? What do we mean by same model multiple times on different data sets?
Yes, sir.
Right. Now the question is, how do we get multiple training data?
So we have done earlier K-fold.
K-fold, okay.
Sampling.
Sampling, yes. The more generalized one is sampling. Okay. Madam, the problem with the K-fold is that if you do take the K-fold, no, that the size will be lesser, right? Size of the data set is less. And anyhow, you have to do it for this testing purpose again within that, right? So how to take multiple training data is the question now. So sir said it is through sampling. Sampling means what? You pick a sample of the data set, right? That means randomly pick a sample from the data set, right? So there are multiple ways of doing it. Bagging follows the concept of random sampling with replacement. And similarly, boosting follows the concept of random sampling with replacement over a weighted data. Random sampling with replacement followed by bagging. Random sampling with replacement over a weighted data is followed by bagging. We'll be looking at these ideas. Don't worry about it. Okay. So the idea is very simple. We get multiple training data sets and then we use this training data set to train multiple models and we combine these models to get a solution or a prediction for the new instance. All right. That is what the idea is. Okay. So let us see the concept of bagging first, then we will go to the boosting. So bagging stands for bootstrap aggregation, which takes the original data set D that contains n training examples. So from the original data set D, it creates m copies of the data set. So given the data set D that contains n samples, it divides this data set into, not divides, it generates multiple data sets, D1, D2, so on, Dm. And all these data sets are generated using random sampling with replacement. So each data set DI is generated by sampling with replacement. So I'll tell you the procedure to generate these data sets. Okay. So let's say that there are n examples or n instances in the original data set. Let's say n equal to 100. It means 100 instances are there in the original data set. Okay. So 100 instances, let us enumerate it to 1 to 100. 1, 2, 3, so on, 100. These are the 100 instances present in the original data set. So now I am generating data set D1. To generate this, pick up one random instance from this 100 instances. So you tell me one random number out 1 to 100. You tell me one number randomly.
57.
57. So you pick the 57 instance, place it in the data set 1 and replace it back. So it means when I say replace it back, it means this is available to pick next time also. So another time, pick another random number 1 to 100. One more random number. 9. 9. Pick another random number, replace it back, pick another random number 1 to 100.
20.
20. So like this. So when you're picking, there is a chance that you pick the already picked instance also. Like for example, 9 we picked already. There is a chance that you pick 9 again after some time, right? So like this process, you repeat it for the 100 times. 100 times. It means 100 instances you are picking by following this random sampling with replacement. So when you are picking the instances with the random sampling with replacement, is there a chance of getting duplicate values or not?
Yes.
Chance of getting duplicate values because you're replacing this back, isn't it? Replacing this instance back, there is a chance of picking it again. So in these data sets, we don't we are having some duplicate values also, not only having the unique values or unique instances, right? So this data set that we are creating is having only 63% of the original data according to some statistics. Okay. So in the similar process, we also create a data set D2. By using the same process, we also create data set D2. It means random sampling with replacement. We apply it for n times and we pick up n instances. And there are some duplicates. So answer to one more question. that suppose I created data set D1 with random sampling with replacement, D2 also with random sampling with replacement. Are these two data sets different or the same?
Different.
Different, because the process is random. You are randomly picking, right? So we get the different instances, right? So these data sets are reasonably different from each other because only 63% of the original or unique examples appear in any of these data sets. So now we got M data sets. Using random sampling with replacement, we created M data sets. Let us call them as D1, D2, and so on, DM, right? So I give this data set to the learning algorithm and I get the corresponding model. Let the underlying model is SVM. Okay, if it is SVM or if it is a decision tree, we get the multiple decision trees. If it is SVM, we get multiple SVM. If it is SVM, let's say, using data set D1, I train SVM1, SVM2, and so on, SVM-M. So like this, multiple models I will get. And I take the average of all these models as the final model. So using this data set D1 to DM, we are training models H1 to HM. And the average model H is equivalent to average of all these models. 1 by M sum over M equal to 1 M HM is the final model. So this is useful for the models with a high variance and noisy data. Why? What do you mean by that? This is useful for the models with a high variance and noisy data. Do you remember the polynomial regression wherein we got very curve, oscillating curve that is oscillating too much between the points?
Yes, sir.
Right. The model with a high variance. Okay. So when you're picking random sampling with replacement, only part of the data that you're getting, I mean, although you are picking up n instances, which is equivalent to the original number of instances, unique instances are only 63% of it. Okay. So let's say with the data set D1, we've got this model. With the data set D2, we've got another model, something like this. Okay. When you take the average of all this, you will get a stable model, right? You see that in the data set, in the model 1, you got peak here. In the model 2, you got a valley here. So when you take the average, what will happen? It will stabilize. So when it stabilizes, there is a higher chance that you get a model which is very much close to the underlying model. Okay. So that is why it is useful for the models with high variance and noisy data, because individually when you look at the models, they are having very high variance, right? But when you combine them, you will get a more stable curve as you see here. Got it, right? Why is it that we have to do this?
Yes, sir. Yes, sir.
Yeah. So Ravi said this partially answers your question, although this is not.
I understand. I understand.
Yeah, not only the answer, but this is one of the reason. Not only the reason. Okay.
Thank you.
Okay. There are other reasons also that we will see as we proceed. Okay. So this we will get a more stable curve as we proceed. That is why it is useful for the models with high variance and noisy data. So we'll see an example that then you will understand it better. Here is an example with the original data set which contains 11 points. 6 of them are from class negative and 5 of them are positive instances. So when I perform the random sampling with replacement, I get this data set D1, D2, D3. 3 data sets we have generated. You see that in each of these data sets, we have only, let's say this is 8 unique examples are there. Some of the examples are repeated twice or thrice. You see that this is indicated with the bold face. It means it came it is picked multiple times. Similarly here, these are picked multiple times. These are picked multiple times, right? So yeah, so this is the data set D1, D2, and D3. According to the data set D1, this is the model that it is learning. And according to data set D2, this is the model that it is learning. According to D3, this is the model that it is learning, right? So when you combine all of them, you will get a model, something like this, that classifies anything that falls here as a positive, anything that falls here as a negative with higher confidence, right? So this is the bagging concept. Okay, is the bagging concept clear? Procedure is very simple. I mean, no confusion also.
Here, you're taking the model weights as average, or you're taking the output average?
Output
Model
average.
output. In continuous, it is average. If it is in the In classifier, it is going to be majority vote, isn't it?
Yeah, both the things works. Okay, so like for example, you take a binary classification problem, let's say. Okay, so let's say that one of the classifier making it as a positive, +1. The other one as a negative. The other one as a positive. Okay, when you take the average, will it be the positive or negative? This is the positive, right? Hello? Greater than 0, isn't it? When you take the average of this is greater than 0, isn't it?
Okay.
So this will be classified as a positive. But what you said is right. I mean, this concept of averaging will not work for all the kinds of data, right? Or all the kinds of discrete data. Because for the binary, it may work. For all the kinds of models, it may not work. In that cases, yes, you are right that voting will work. Yes, sir. Shall we move on?
Sir.
I
Yeah,
have one more doubt.
Madam, please. Ramya, madam.
Sir, where there are many regions in this location, no, sir? How we will get which is the positive region, which is the negative region?
No, actually, I mean, it is indicated like this in the figure, right? But whatever majority of them will be classifying it as, like, say, let's say that, let's say the point that belongs to somewhere here. Okay. Okay. How is this model classifying? This is classifying it as a negative. How is this model classifying? It is classifying it as a positive. How is this model classifying? It is classifying it as a negative. Okay. So majority is negative. It will be classifying it as a negative.
Okay, sir.
Yeah. Um, one more point. All right. So let us summarize the procedure. Okay. So you have given the original data set D. From this, you are creating M copies of the data set D1, D2, so on, Dm. Using these data sets, you are building M hypothesis H1, H2, so on, Hm. Okay. And the final model is the average of all these models. Isn't it? Very simple process. All right.
Last one. Bootstrapping, clear cut one definition.
Bootstrapping.
Yes,
What
sir.
is boosting? Boosting. You are saying boosting. Bootstrapping. Okay.
I think GVA, please kindly mute yourself.
Bootstrapping is kind of, I think, bootstrap aggregation. So bagging stands for, what is that bagging? Bootstrap aggregation. Okay. So that is why it is bootstrapping. Okay. So 3 data sets via bootstrapping. That means that process I've told you, no, random sampling with replacement. This is equivalent to this set.
Okay, sir.
Yeah.
Thank
you. Yeah. So is the process clear? The 4 steps?
Yes, sir. Yes, sir.
Yeah. Now, the next algorithm is random forest algorithm. Random forest is a kind of ensemble learning technique only, and it is a kind of bagging also. Okay. But slight difference between the traditional bagging technique and the random forest is that here in random forest, it performs random sampling on the features, not on the instances. So in case of bagging, how are you performing random sampling? Randomly you are picking up one instance and placing it in the data set, right? So you're picking another instance, placing it in the data set and so forth, right? So in case of random forest, you perform random sampling on the features, not on the instances. So let's say that there are 100 features, attributes, 100 attributes. Each instance is described of the 100 attributes, A1, A2, so on, A100. Okay. So it randomly picks 10 attributes. Okay, and it also has the corresponding label Y. It randomly picks up 10 attributes. Let's say randomly pick A2, some A15, A20, something like this. 10 attributes it picks up. And then corresponding target variable it takes. This one, last column. It trains one decision tree 1. Next time it picks up a different 10 attributes, right? 10 attributes again, let's say A1, some A12, something like this, 10 attributes. And together with the target variable, it trains a second decision tree 2. So this process is repeated multiple times. So with each one of this data set, we get a one decision tree. Because we are training multiple data sets, we get multiple decision trees. So group of all these decision trees, we call it as a forest. Okay, random because we are randomly picking the attributes and then training the multiple decision trees. That is why it is random forest. So
Sir,
now, yes.
sir, in that case, you are choosing the instances randomly. Here, in this case, you choose attributes randomly. That is the difference.
Attributes randomly, yes, exactly.
Thank you, sir.
Okay, so now given a new instance, how to classify it? Okay, I know a lot of noise is coming, right?
GVI is unmuted.
I'm muted. Okay, so let us see. Yes. So now to classify a new instance, I give it to all these the decision trees. So and take the majority voting if it is a classification problem. If it is a regression problem, we take the average. So prediction of the test example, votes on or averages, prediction of Rama, all the decision trees. Okay. So it is a simple extension of the bagging concept. So in case of traditional bagging technique, we randomly choose instances. In case of random forest, we randomly choose the attributes to create multiple data sets. In both the cases, we are creating multiple data sets using the given data set. Clear? Random forest? Clear, right?
Yes, sir.
Yeah. Yeah.
Sir, can
So-
you please repeat, sir? Excuse me, sir.
Yeah, sure, madam. So in bagging, what are we doing, madam, to create multiple data sets? We are randomly picking the instances and placing that in the data set, isn't it? And like that, we are repeating the process for multiple times and creating multiple data sets.
Yes,
Am
sir.
I right, madam?
Yes,
So
sir.
here, instead of picking the instances, we pick the attributes randomly. So let's say if there are 100 attributes and the target variable, one output variable. Randomly, we pick 10 attributes. Together with the output variable, we create one data set. Next time, you pick different 10 attributes, and then together with the target variable, you create a second data set. Repeat the process for multiple times, you will get multiple data sets. Got it, madam? So
Yes.
with the multiple data sets, you train multiple decision trees. All these decision trees together forms a random forest. To classify a new instance, give it to all these decision trees and take the majority voting or averaging. Majority voting if it is a classification problem, averaging if it is a regression problem. Clear, ma'am? Who has asked this? Ramya, madam?
Yes, sir.
Yeah. Okay.
Sir, we are training instances as it is, sir. No, like.
Yeah, number of instances are all the same. Only the attributes will be different.
Okay. Then the average.
I mean, it means in every one, all the n instances will be present in all the training data, but all the attributes will not be present. Only part of the attributes will be present.
Sir, actually, two people are listening from one system. That's why different voices, sir. Shafia Sheikh and Geeta. I have registered, sir.
No problem, no issue. I'm not. That's okay. Fine. Is it okay, madam? Is it clear? Shall we move on?
Yes, sir.
Yeah, yeah. Actually, this is one of my favorite topic, ensemble learning. Okay, actually very interesting topic. Very interesting topic to teach also. So you will also enjoy, I hope. Okay. So the next one is boosting. Boosting. This is also one of the very interesting idea. Bagging is very simple, but the boosting also simple only, but slightly different idea. Okay. You will enjoy this. Okay. Idea is very simple. Take a weak learning algorithm, turn it into awesome one by making it focus on the difficult cases. Only requirement to choose the algorithm is that it should be slightly better than the random model. You know random model, right? What is random model? If you take the classification problem, what is random model? Randomly pick some label and predict that as a label. Let's say that there are three classes, right? Randomly assign some label to each and every instance. That is also getting some accuracy, right? By chance it may hit. Hello, following?
Yes, sir. Yes.
Right. By random chance also it may be having some hits, right? So it has also got some performance. So only requirement to pick the weak learning algorithm is that it should be slightly better than the random model, right? And you turn it into awesome one by making it focus on the difficult cases. It's like this. I hope most of you are like teachers, as it sounds like that to me. Okay, Geeta madam, Ravi sir, others.
Yes, sir.
Yes, sir. Yes, sir.
Yeah. So you take a weak student and turn him into an awesome student by focusing on his weak areas. Suppose the student is weak in English, you train him in English. If he is weak in communication, you train him in communication. If he is weak in mathematics, you train him in mathematics. If he is weak in programming, you train him in programming, right? Finally, you turn him into an awesome one. Similar way here also. Take a weak learning algorithm, turn it into an awesome one by making it focus on the difficult cases. Okay. So most of the boosting algorithms follow these steps. What is that? First step, train a weak model on the some training data. After that, compute the error of the model on each and every training example. After that, give higher importance to the examples on which the model is making a mistake and retrain the model using the important weighted training example and repeat the process for multiple times. Okay, and most of the models naturally allow learning from importance weighted examples. So this at this point, I hope you might have got only 10% of the algorithm. Okay, I don't expect more than that. Okay, so let us proceed further, then you will understand. So this is the algorithm, but this looks so scary because of so much mathematical notations in it. So I'll not discuss this right now. Let me discuss the example first, then I will come back to this algorithm later. Okay, so the procedure is like this. You take a weak learning algorithm and turn it into awesome one by making it focus on the difficult cases. So initially you take the given data. So this is the given data in which we have 10 training examples. 5 of them are positive and 5 of them are negative. And the weak model that we are choosing here is the axis parallel linear classifier. Axis parallel means it should be either parallel to x-axis or it should be parallel to y-axis, right? So this is the axis parallel linear classifier. Because of this axis parallel restriction, this is a weak classifier. Axis parallel linear classifier. All right. So this is the weak model that we are choosing. So initially, this is the data set given to us. Initially, assign a equal weightage to each and every example. Equal weightage means as there are 10 examples, 1 by 10 weightage for each and every example. So 1 by 10 weightage, 1 by 10 weightage, 1 by 10 weightage, and so on. Okay. So generally, how do you define a loss function? How do you define a loss function? Tell me the loss function of the linear regression model. How are you defining loss function? 1 by 2m sum over I equal to 1 to m h theta of xi minus y. isn't it? Hello? Do you
Yes,
remember
sir.
this?
Yes, sir, yes.
So here you are giving equal importance for all the examples. Okay. Suppose if I give you weighted data in the sense for each and every example, there is a weight associated with it. Okay. And I ask you to reduce the weighted loss. The objective is to reduce the weighted loss. Then we define a loss function something like this, right? Sum over I equal to 1 to m, weight of the ith instance times the corresponding loss, h theta of xi minus yi whole square. Am I right? Right. If there is a setting of multiple different weights for each and every example, we multiply the loss with the corresponding weight and we reduce the weighted loss. Hello, am I right?
Yes,
Yes,
sir.
sir.
Yes. So now initially we give equal weightage, but we modify the weight as we proceed. How we modify, we'll see later. Okay. So this is the equal weightage that we are giving. And now learn a hypothesis that minimizes the weighted loss. Learn a hypothesis that minimizes the weighted loss, right? So let us the hypothesis is this. Hypothesis H1 is this as per the weightage given in the previous slide. How many misclassifications? If this is the hypothesis, how many of the instances are misclassified?
3.
3 are misclassified. 3 positive instances are misclassified. Now what we do is that we increase the weight for these misclassified instances and decrease the weight for correctly classified instances. Why is it so? Because these are the instances that the existing model is failing. Our existing model couldn't do well. So the task of the next hypothesis is to compensate the shortcomings of the existing hypothesis, right? And rest of them it could correctly classify. So you can less focus on them and more focus on this incorrectly classified instances. So to pass that knowledge to the next hypothesis, we are increasing the weight of this incorrectly classified instances and decreasing the weight of the correctly classified instances, right? That is indicated with the size of the instances. Size is more means the weight associated with them is more. Size is less means the weight associated with them is less, right? So what are we doing here? We are upweighting all the incorrectly classified instances and downweighting all the correctly classified instances. How we are upweighting and downweighting we'll see later. Don't worry about that part now. Just get the procedure first. Okay. So what we have done so far? Initially, we have assigned equal weightage for all the examples. As per that weightage, we learned the hypothesis and computed error of each and every example. If it is misclassified, then we are upweighting the corresponding weight. If it is correctly classified, we are downweighting that weight. So is it clear so far?
Yes, sir. Perfect, sir.
So now with this new weightage, learn a hypothesis that minimizes the weighted loss. With this new weightage, learn a hypothesis that minimizes the weighted loss. And let the hypothesis is this. How many are misclassified according to the second hypothesis? 3 are misclassified. All of them are negative. Now again repeat the process. Upweight all the incorrectly classified instances and downweight all the correctly classified instances. And with this new weightage, learn another hypothesis that minimizes the weighted loss. Okay. So here is the new hypothesis, and according to this also 3 are misclassified, 2 are positive and 1 is negative. Suppose you decided to stop at round 3. It means your ensemble now consists of 3 hypotheses, H1, H2 and H3. Okay, so aggregate them. So when you are aggregating them, you have to give the importance to each and every classifier. How do you give the importance? Importance is based on the mistakes that the model is making, right? So it means you see that here it is making 3 mistakes. 3 mistakes it is making, but the weight associated with each and every example is 1 by 10. So total mistake that it is making is 3 by 10, right? So because the weight associated with this 1 by 10, so 1 time 1 by 10, weight associated with this is 1 by 10, weight associated with this 1 by 10. So total 3 by 10 mistake it is making. So it is making an error of 0.3. So compute the corresponding importance in such a way that as the error is lesser, importance is higher, right? So compute the importance associated with it. So don't worry about the how to compute the importance also for now. Just understand that according to the error, we compute the corresponding importance. Okay. So this error is the relation between error and the importance is indirectly proportional. It means as the error decreases, importance will increase. Or if error is increasing, the importance will decrease. These are inversely proportional to one another, right? So like this, you compute the importance for each and every hypothesis based on the mistakes that it is making. Now, the final model is the weighted average of all these individual models. So this is the importance of the first model times the corresponding output. Importance of the second model times the corresponding output. 0.92, this is the importance of the third model times the corresponding output. So when you combine all these models, you will get this model. It means anything that is falling in the blue region will be classified as a positive. Anything that is falling in the red region will be classified as a negative. So it means if you look at the individual classifiers, they are looking very weak. They are axis parallel lines, right? They are weak models. But when you combine them, you are getting a strong non-linear classifier. So multiple weak linear classifiers are combined together to give a strong non-linear classifier, and that's the beauty of this ensemble learning technique. So individually they are weak and linear. When you combine them, it is forming a strong non-linear boundary as you see in this figure. All right. So have you got some idea about this boosting?
Yes, sir, we understood.
Yes.
But when to stop this process of
That is the number of iterations is a kind of hyperparameter, sir.
okay.
And depending on the termination condition, one of the simple termination condition is number of iterations. Okay, so that is the parameter to tune, hyperparameter to tune. I mean, you have to do it through trial and error. Yes.
Okay. Thank you, sir.
Okay, so now have a look at the algorithm. Then we will go through the example one more time. Okay, so we are given a training data x1, y1, x2, y2, so on, xn, yn, where xi is the d-dimensional feature vector, yi is either -1 or +1. It can be easily extended to the multi-class also, very easy, not at all a problem. If you understand this process, you will only extend it to the multi-class. Okay, so this is the data set given to us. We initialize the weight for each and every example. So initially, data set D1 is having equal weightage. Data set D1 is the data set at the first iteration, right? So equal weightage, 1 by n weightage for each and every example. Okay, so we learn a weak classifier or weak hypothesis using the training data weighted as per the corresponding data set, weighted as per D1 initially, right? So as per this new, as per the weightage, given weightage, we learn a hypothesis that minimizes the weighted loss. Okay. So after that, we compute the weighted fraction of errors of this hypothesis. It means we compute the weighted fraction of the errors made by that hypothesis. It means, like, for example, you see this example. How many mistakes that it is making? 3 mistakes it is making. So we take the weight associated with each and every mistake, each and every example, right? So 1 by 10, 1 time 1 by 10, plus 1 time 1 by 10, plus 1 time 1 by 10, total 3 by 10. It means if a model is making a mistake, the corresponding indicator is 1. If the model is not making mistake, the corresponding indicator is 0. So 0 multiplied by 1 by 10 is also 0. Okay, that is what it is computing. So dt of n is the weightage, and this is the indicator, whether it is the correct or wrong. If it is correct, the indicator is 0. If it is wrong, the indicator is 1. It means all the incorrect instances are corresponding weight. We are taking summation over all the incorrectly classified instances weights. Okay, that's how we are computing the error, right? Once you get the error, compute the corresponding importance. Okay, so importance of the hypothesis T is indicated with alpha T, which is equivalent to half log 1 minus epsilon T by epsilon T. Okay, so let us try this. when epsilon equal to 0 or when epsilon equal to 1, what is this value? This gets larger as epsilon t gets smaller. So this importance is designed in such a way that as the epsilon t gets smaller, this alpha t gets larger, right? They are inversely proportional to one another. That we will see in the example also later, right? So far is it clear? These 3 steps clear?
Yes, sir.
Yeah. So now update the weight for each and every example. How we update? We decrease the weight for correctly predicted examples and we increase the weight for incorrectly predicted instances. How do we decrease or increase the weight? To decrease the weight, what we do is that we divide the previous weight with e to the power alpha t. Alpha t is the importance that we have computed. To decrease the weight, we divide this previous weight with e to the power alpha t. It means we are multiplying it with e to the power minus alpha t. Okay, it means it is equivalent to dividing it with e to the power alpha t. This is what we do to decrease the weight. To increase the weight, we multiply the previous weight. We multiply the previous weight with e to the power alpha t. To decrease the weight, we divide it with d to the power alpha t. To increase the weight, we multiply it with e to the power alpha t. E is the base of the natural logarithm, which is 2.71. Okay, so got it? How to update or how to downweight, how to upweight or how to downweight? The 4th step. Clear?
For alpha TT, what is that? Is it?
T is the round number, sir. Data set at round 1, round t. I mean the iteration t. If it is the first round, it is data set 1. If it is second round, data set 2. What is the difference between data set 1 and data set 2? Weights.
Weight. Increase the weight or decrease.
Yeah, yes. Weights will change. Examples are the same, but weightage corresponding to them will be different.
You mean to say that when it goes to next iteration, the instances, I mean to say that weight gets changed in the next instance.
Weights will change. Okay, as per the importance that we are giving for that example. Either we have to give higher importance or lower importance. It means the kind of knowledge that it is transferring to the next hypothesis. Okay. So in a sense that it is giving a hint that where you should focus more.
Sir, you mean to say you have to take the model and wait for each iteration, and we have to average.
Each iteration, the model will also change, and the data points weightage also will change. Please ask, sir. If you have any query, you can ask. Clear? If it is not clear, I can repeat also.
It should be known. That is hyperparameter. You are saying.
Which one? Number T, capital T. Yes.
Sir, when we are increasing the weight, are we really dealing with the scalar values or just the importance wise?
Scalar values only.
Okay.
Importance only. This is importance also, or just the scalar value also. See, when you give more weightage to an example, obviously, what is your objective? Objective is to minimize the overall loss. And loss is associated with the corresponding weights only, right? So it means obviously it is giving more importance to the highly weighted data points. And you are reducing the weighted loss.
And when the weight are increasing, again the value scalar wise it is increasing. Then again they need to get normalized.
That normalization part is different that I will talk about now. I haven't come to that step. You are talking about this step, right?
Yes.
Are you talking about this step? Normalize dt plus 1. That is
Yes,
different.
sir.
Don't worry about that. I will explain that. That's different. Why to normalize, I will explain. But you see this. Here equal weightage. So after one round, weights are changed. Now the data set is changed, right? So as per this new weights, when you are trying to learn a hypothesis that minimizes the weighted loss, you got a different hypothesis now, isn't it? Why is the hypothesis changing now?
Sir, one more doubt, sir.
Please answer to this question. I'll take your doubt. Please try to complete this part and then take up a next question. Before, with equal weightage, you got this hypothesis. Now you changed the weights and you got this hypothesis. Why is that hypothesis changed?
Data set is changed.
Because
Data
the
set
value
is-
gets changed.
Suppose what happens if I learn this hypothesis now also? I mean, if this is the hypothesis, what will happen? The loss will be more, right? Because this classifying these three instances incorrectly. If it classifying these three instances, weight associated with them is more. It means it is making more error, more loss, right? But the objective is to minimize the overall loss, right? Overall weighted loss. So it is learning this hypothesis such that it minimizing the overall weighted loss, because the mistakes that it is making, the error associated with them is less. Got it, madam? So as the data changes, the hypothesis will also change, because the objective of the hypothesis is to minimize the weighted loss. You're not giving equal importance for all the examples, right? So the loss you are computing based on the weight associated with each and every example. It means you're computing loss associated with each and every example and multiplying that loss with the corresponding weight and trying to minimize the overall loss. So learning hypothesis in such a way that it minimizes the overall loss.
Sir, you mean to say H1 is transforming into H2 with the
No.
weighted.
Yeah, that we will see later. Yes,
Is it
I
like
mean,
you
you'll be
choose?
that we will be updating it, sir. That we will be seeing it later in the gradient descent algorithm, how we update. But for now, you see them like the different models only. For now, you see them like different models only. This is a separate model. This is a separate model. Okay, till you get the idea, you see them like a different models only, different hypothesis only. The data is transforming. Okay, data is transforming. This is the different weight. This is the different weight, and this is the different weight from that. So weights making the different data sets different. Got it, sir?
So go to previous slide. Sorry, you mean to say the previous yeah. You mean to say the weights are actually in the decay function. They are following exponential. I mean decay function, isn't it? Whether it is increasing or decreasing.
It is multiplied with e to the power alpha t, sir. E to the power means 2.71 to the power alpha t.
Like decay function, sir. Weights.
What is that?
Decay. Oh, yeah. Decay function.
Where is that, sir? Decay. You're asking about this?
Yeah. Exponential function we are using. Weights are actually following the decay function. That is exponential function. Yeah. Sir, another practical issue I think is how do we tackle the floating point number, because as and weights are data sets are more weights actually associated. If you are saying 1,000 I mean, how do you factor in all the that problems? We have to convert that to log, or how do we take that? Because floating point, if it is too low, we cannot able to represent it.
Can you repeat it? You mean to say that weight is very low?
Yeah, when it is correctly classified, weight will go actually decreases to an extent where we cannot represent that that as a floating point. How do we take care? Do we need to use any
We'll
log?
do normalization. I'll come back to that point. Okay. But have you understood till this point? If you see the example one more time, no, I think all of your doubts will be clear. Okay, so please, I mean, if you are getting the process, okay, we'll go to the algorithm and go through it once, then you will understand everything. Okay.
Yes, sir.
So till here you understood, right? The process. Okay.
Yes, sir.
Yeah. So now what we do is that we normalize all these weights so that it sum up to 1. Initially, when you take equal weightage 1 by n, 1 by n, so 1 by n plus 1 by n, so on 1 by n, like that there are n examples. So n times 1 by n, total equal to 1. So it means overall weight must be equivalent to 1 to get the proportion or the fraction of this example share in that weight, right? So to do that, what we do is that we take each weight in the numerator divided by sum over all the weights. So to compute the weight of a particular example n, we take the weight associated with that in the numerator, sum over all the weights in the denominator. So this will bring sum over all the weights to 1. Okay, sum over all the weights to 1, right? And the output is the aggregation of all these individual hypotheses. This is the process. So we'll see the example, and after that, if you have any doubt, I will take. Don't worry about it. Okay. So I hope the procedure is clear. Okay, so shall we move on to the example?
Yes, sir.
Yes, sir.
So this is an example. There are 10 instances. So what is the initial weight for each and every example? 1 by 10, right? 1 by 10 is the initial weight. So with this weightage, learn a hypothesis that minimizes the weighted loss. So let the hypothesis is this H1, this H1. So it is making 3 mistakes. And you know the weight associated with them is 1 by 10, 1 by 10 and 1 by 10. So the total error that this hypothesis is making is 0.3. 0.3. Now compute the importance of this model using this error. So half log 1 minus epsilon 1 divided by epsilon 1, which is 0.42, which is the weight associated with hypothesis 1, which we indicate with alpha 1. So now increase the weight of all the incorrectly classified instances, decrease the weight of all the correctly classified instances. How we increase? To increase the weight, we multiply the previous weight with the e to the power alpha 1. To decrease the weight, we divide the previous weight with e to the power alpha 1, or we multiply it with e to the power minus alpha 1. Right? So
Sir,
here is there
excuse
is a
me.
mistake.
So we have already discussed this, no, sir? Example.
Yeah, we discussed this example, but not with respect to the weights. We just discussed that generally that we have to increase weight or decrease weight. But how to decrease, how to increase, we didn't discuss. Okay. So for each misclassified point, we upweight by multiplying it with e to the power alpha 1. There is a mistake in the slide. Please correct that. E to the power alpha 1 here, not alpha 2. And decrease the weight by multiplying it with e to the power minus alpha 1. Now we got the new weights, and these are indicated with this. Weights are indicated with the sizes. Size is more means the weight is high. As per the new weightage, you learn another hypothesis that minimizes this weighted loss. That minimizes this weighted loss. And this is the hypothesis that it is learning as per this new weightage. And this is also making 3 mistakes. But the weight associated with them is less than 1 by 10 because we decreased the weight, right, in the previous iteration. So here the error we have got is 0.21. So earlier 0.3, even if it is making 3 mistakes, it is 0.3. Now also it is making 3 mistakes, but it is just 0.21. Why is that? Because weight associated with these examples is less, right? So the error associated with this hypothesis is 0.21. Now compute again the importance of this hypothesis, which is 0.65. So I want you to make note of this point, that when the error is 0.3, the importance is 0.42. When the error is 0.21, importance is 0.65. It means as the error is decreasing, the importance is increasing. Agree? Agree to this point? As the error is decreasing, importance is increasing. Is that point clear?
Yes, sir. Yes, sir.
Yeah. So as the error is decreasing, importance is increasing, right? So now again, repeat the process. Upweight all the misclassified instances by multiplying it e to the power alpha 2. Downweight all the correctly classified instances by multiplying it with e to the power minus alpha 2. Now this is the new weightage, right? So with this new weightage, again learn a hypothesis that minimizes the weighted loss. right? And now again compute the error made by this hypothesis. Now also it is making 3 mistakes, but the weight associated with them is very small. That is why the error is 0.14. Now again compute the importance. Importance is 0.92. You see that here also the error is reduced further, importance is increased further, right? So suppose you decided to stop here. Now you take the 3 hypotheses and multiply them with the corresponding weights. So what is the weight associated with the first one? First hypothesis 0.42, right? Times hypothesis 1 of new instance xn plus what is the weight associated with the second hypothesis 0.65 times h2 of xn plus 0.92 multiplied with hypothesis 3 of xn. Okay, so this is the new hypothesis. 0.42 times the hypothesis 1, 0.65 times hypothesis 2, and 0.92 times hypothesis 3, and the sign of it is the final prediction. So right. So now suppose if there is a point somewhere here, how this classifier 1 is making this. So let's say the point is somewhere here. Okay. So what is the prediction of the hypothesis 1? Negative or positive?
Positive.
Negative, no.
Oh,
All the blue
okay.
color
Okay.
is
First
in
one
this
is
one.
negative.
Negative 0.42 times plus 1. What is the prediction according to this? Positive, right? 0.65 times plus 1. Sorry, this is minus 1, right? This is negative. It's classifying as negative. How is this classifying?
Positive.
Positive. 0.92 times plus 1. Right. So what is the resultant? Will it be positive or negative? When you take the sum over all this, it will be positive. Therefore, it will be classifying it as a positive. Okay. So according to this algorithm, anything that is falling within this blue region will be classified as a positive. Anything that is falling within this red region will be classified as a negative. It means the decision boundary this ensemble is learning is this decision boundary, which is non-linear in nature. It means what? Multiple weak learners combine together to give a strong non-linear classifier, and that is the beauty of the ensemble learning that I am saying. Clear right now? Any query you can ask now. Geeta madam, go ahead. If you have any.
Yes, sir.
Yes, sir.
One doubt, sir. So if a new instance comes, that weight of this new instance will be 1 by 10 only. Is it, sir?
No. We don't require any weight now to classify a new
For
instance.
example, when a new instance comes, how it classifies, sir?
That's what I'm saying. I gave example now. No? Let's say example here. Let's say the example is somewhere here. New example. How
Yes,
this
sir.
is classifying? Give it to this. How is it classifying? Negative or positive? This
Negative,
one.
sir.
Negative, right? So 0.42 times negative.
Hmm.
How is this classifying?
Negative.
Negative. 0.65 times negative. How is this classifying?
Positive.
Positive. 0.92 times plus 1. So what is the
Oh.
majority domination? Weightage
Negative.
for the negative or positive?
Negative.
Negative. So it will classify it as negative.
Okay. Understood. Those values, whatever you have computed, that will be hypothesis values will be there on stored
There.
here.
Yeah.
Okay.
That's the-
So it is similar to the in the neural network. You keep the weights similar to that. You will have the value here. Am I right, sir?
Yeah, but it is slightly different. We can't say that. So, we have also something called mixture of experts that is similar to the neural network that we're going to see.
Okay.
Briefly.
Thank you, sir. Thank you.
But is this idea clear to everybody? Boosting?
Okay, sir. Okay, sir.
Okay. So the idea is very simple. You are learning a weak classifier at every stage and computing the error. You are introducing another weak classifier to compensate the shortcomings of the existing weak learners. Right? And the weakness of the existing classifier or the shortcomings of the existing classifier are identified through the weighted data points. That's all. Very simple process. So here is another example. So there are two classes. One class is indicated with blue color, another class is indicated with a red color. What is your opinion? Is this a linear data or non-linear data? Linearly separable or not linearly separable?
Non-linear.
Non-linear, right? You can't draw a line that separates the blue instances from the red instances, right? So if you use any perceptron or a linear classifier, it will not be able to separate. Okay. So, but if you use the ensemble learning technique, at the first stage, you may be learning some model like this. Now up weighting, down weighting. So as per the new weightage, you learn another classifier. You will get this classifier. Again, up weight, down weight, learn another classifier. You will get at round 5, at round 7, at round 40, you got this. So a single linear classifier couldn't separate these blue instances from the red instances. But multiple such linear classifiers combined together is forming a non-linear decision boundary, as you see in this figure. Right. So that is the advantage of this ensemble learning techniques. Okay. Clear? Understood? So far, we have discussed it. Clear, right? Any query so far you can ask?
No, sir.
Yeah. So, so far we have discussed two things, majorly, bagging and boosting. So, which is best? There is no clear winner. Okay. Usually depends on the data. So it is the same answer everywhere. Okay. So you ask me which is the best, you can't say that. Okay. So bagging is computationally more efficient than boosting. Okay. Why is it so? Why bagging is computationally more efficient than boosting? In case of bagging, once you create m copies of the data set, you can train m models simultaneously as they are not independent, as they are not dependent on one another. Am I right? Once you create m copies of the data set, you can train the individual models parallelly or simultaneously, right? So, but then is it possible in case of boosting? Is it possible to train m models simultaneously in case of boosting? Not possible, right? Because
No.
the weight of the data set D2 depends on the errors made by the hypothesis 1. How will you make hypothesis 1 and 2 parallelly? You can't build them parallelly, right? Because weightage that you are assigning at a particular stage is depending on error made at the previous stage, right? So then they can't be trained independently. That is why bagging is more computationally efficient than the boosting. Okay, so both of them reduce the variance by combining the different models, but bagging usually cannot reduce the bias. It means if you are learning some simple model, it cannot reduce the bias. Like it means underfitting case, it cannot handle. If the model is underfitting, then even if you combine multiple such underfitting model, you will get the underfitting model only. But if it is overfitting, even when you combine the multiple overfitting model, you will get a stable curve and you can solve the variance problem, right? So bagging usually cannot reduce the bias, but boosting can reduce the bias. So bagging usually performs better than boosting if we don't have a high bias, only want to reduce the variance. It means if we are overfitting only, in that case it helps. All right. So this is the comparison between bagging and boosting. There is another method which is a mixture of experts. So like sir, you said no, that can we have a neural network kind of. So give the data set to the multiple experts. You can see the multiple experts like the multiple models. And when you're combining these multiple models, what weightage that we give to the individual models is learned through a gating network so that it minimizes the loss between the prediction and the actual value. So these weights are learned through a gating network. So you're modeling it as a neural network and then you're learning this weight so that it minimizes the difference between actual and the predicted values. Okay. So this is the gating network or the neural network that you can imagine it like a neural network, but not the previous one, sir. So although there is a weights associated with the models, the way that you're computing the weights is different there. It's not through the learning process. It is through some example, intuitive way of computing that weights there, not through the gating network or
Okay.
the neural network. Yes. Okay. Okay. So to summarize whatever that we have discussed so far, complex learning problems can often be solved by effectively combining multiple weak models via ensemble learning methods. So we have looked at some of the representative ensemble learning methods. We have seen some simple ones like voting, averaging, or stacking. We have seen some complex models like bagging, random forest. We've also seen boosting, Adaboosting. We have seen whatever the boosting technique that we have discussed, we call it as the Adaboosting technique. Like that, various other boosting techniques also there. Gradient boosting, what is that? XZ-boost. Like that, various boosting techniques are there. We have also seen mixture of experts. So these models help to reduce the bias, variance, or both, leading to better test accuracies. So is it clear to everybody so far?
Yes, sir.
Yes, sir.
Sir,
So,
in the previous slide, one small point, sir, that gate term has come now, sir. Previous, yes. Gating network, in the sense there will be some logic gates will be used, sir, to.
no, madam. You can imagine like a artificial neural network. I mean,
Okay.
that weight that you give to the individual experts is decided through that loss. I mean, that by minimizing the network loss. Okay, it means you here the objective of the network is to minimize the difference between actual and the predicted values. So for which weightage it is minimizing the difference between actual and predicted values, those weights we will fix. It means they are also learned through a learning problem, not something we are assigning randomly.
Okay.
Yeah. Any other query? So if you have patience, if you don't have patience, we'll stop here. That's okay. I mean, it gives you some more idea about ensemble learning. If you have patience, I will discuss the, sir, please.
If you discuss that, you'll get confused, sir, because we have understood these things properly. And now,
Okay.
if we
Gradient
get
boost.
gradient
Okay.
boosting, I think it requires time for us to understand all those last 4 modules. I think 4 concepts.
Okay. Up to you. If you want, I will continue. Otherwise, we'll stop here.
But we understood very nicely. You have presented very nicely. It was
Sir,
great.
any examples, sir, with code?
That I will demonstrate. Okay. But shall we proceed with the gradient boosting or not? You have to decide now.
So you take majority voting.
We'll have it in the next class because already it is
Burden. Okay.
burden. Don't say already we have loaded, sir. I mean,
Overloaded.
got whatever we require.
Show the demonstration, sir. That will give you more
Okay.
ideas.
What about tomorrow's session? We are meeting tomorrow, right?
Yes, sir, sure.
Shall we have it in the morning, sir? Morning or evening, sir? Is it possible?
Morning is okay for me. I don't have any meetings. Okay, except for the fact that I have to get some vegetables. Otherwise, I'm free after 8:30. But 3 to 5, I have one again. I mean, one meeting. 3 to 5. So except for that timing, anything is okay.
You decide, sir. Okay.
But don't you cook chicken in the morning tomorrow?
Shravana Masa, sir.
Oh, okay.
Shravana ends, sir, today. There is no Shravana.
Sir, Ganpati, we have to welcome, sir.
Okay. What is this? Okay. Bagging. So the same thing, sir. Okay, that 6-step process. First step is import the required libraries. So importing all the required libraries. Okay. So here is this, pandas is to that read that data set. Okay. This is the base model that we are choosing. Support vector classifier. All the ensemble learning techniques are here, sir. sklearn.ensemble. So from this, I'm importing bagging classifier. Okay. And after that, from sklearn.metrics, I'm importing classification report and the confusion matrix. Classification report and the confusion matrix. These are the evaluation metrics. This is the train test split that you know the functionality of it. So only new thing that we have imported is this bagging classifier. Similarly, if you are applying it for the regression problem, you can import bagging regressor also. Okay. And if you want to check all the ensemble learning techniques, just go to sklearn.ensemble. Type sklearn.ensemble in Google and click on very first link. You will see ensemble learning techniques available. Okay. So now the second step is read the data set. We are reading this bill authentication.csv. This file is also shared, right? This is a kind of banking data. So I'm just printing the banking data.shape and head to show you how the data looks like. So this is how the data looks like. There are 4 attributes: variance, skewness, kurtosis, and entropy, and the class label. Class label is either 0 or 1. Okay, it slightly came to the next line. Okay, but this is a class label 0 or 1, the last one. The one that is coming to the next line is 0 or 1, right? So now that is how the data looks like. Now prepare the data set. Just drop the last column. Remaining columns will give you X. Just access the last column, that will give you Y. Now fourth step is to split the data set into training and testing. Right. So this is splitting the data set into training and testing. And after that we get the training data and testing data. Now build the model. To build the model, you're calling the bagging classifier. You need to call the base estimator. Base estimator is, this is the model, SVC. This is the base classifier or the underlying model, we call it as. And number of estimators is 10. It means 10 data sets you will be creating if the number of estimators is equal to 10. So this is the model. You got the model, fit it for the training data and predict for the test data. Only this step will vary slightly, sir. Otherwise, the rest of the things are same. Model.predict X test. This is the confusion matrix and classification report that you are printing. Right. See that, except for the 3 examples, most of them are correctly classified. You can try with the by varying the number of estimators also.
So once again, that n estimators, they are what, sir? Number of
estimators, madam. It means in bagging, we are creating m copies of the data set, no?
Okay.
So that m is this. If you give 10 copies of the data set will be created. If you give this number of estimator equal to 5 copies of the data set will be created. This is bagging. Okay. I have a gradient boosting also. Okay, not Adaboosting, but you can import the Adaboosting classifier, Adaboosting regression also equivalently. Let me demonstrate gradient boosting so that you will get some more idea about. So gradient boosting, same thing, importing the packages. So here we are importing gradient boosting regressor. I directly imported ensemble, but I'll be calling ensemble.gradient boosting regressor. Okay. Similarly, you can call Adaboosting regressor also. That is up to you. So I directly imported ensemble, but not required actually. sklearn.ensemble, you can import gradient boosting regression. And directly imported linear model. Instead, you can import the linear regression model. Okay, whatever is comfortable. So this is the synthetic data set we have generated, and the data looks something like this. So what is your opinion? Is this linear or non-linear? Pattern. Can you capture the pattern through using a line?
No, sir.
No, right? So if you call the linear regression model and fit a linear regression model to the data, model looks something like this. Okay, so which is not a good fit for this data. So if you compute the residuals are very high. It means the difference between the actual and the predicted values is this. This is very high. Now I am applying gradient boosting regression. These are the parameters required by the gradient boosting regression. So don't worry if you don't understand some of the parameters, because we haven't discussed this gradient boosting regression yet. Okay, that we will discuss later. Or even if I don't discuss, I will share the slides. You can go through them. So number of estimators is 1. Maximum depth is the complexity of the model. So this is like a regression tree that you are giving as the underlying model. If you increase the depth, then the complexity of the model is high. If you are giving the depth of 1 means it is a very simple model that you are giving. And learning rate is that alpha, which is 1, and the criterion is MSE, mean square error. You want to minimize the mean square error. So with these parameters, you're calling gradient boosting regression from ensemble. All right, model.fit, right, and model.predict. You're plotting the model.predict. So you see that this is the model that we have got. Little better, right, as compared to the linear regression. Little better, slightly better. Hello? Overloaded? Anybody? No? Not following? Am I audible?
Yes, sir.
Not following?
Following, sir.
Okay. Sir, what about you? I mean, are you guys following? Ravi sir?
Yes, sir. Yes, sir.
Yes, sir.
Thank you. Yes. Now change the number of estimator to 2. Rest of the parameters are the same. Only the number of estimators you are increasing to 2. Again, train the model, fit it for the training data, predict for the test, predict for the same data. So here is the model, slightly improving. So let us try the different number of estimators. So I will return it in a loop. Number of estimators 5, number of estimators 10, number of estimators 20, 50, and so forth. I mean, like that we are training multiple. You see that this is with the 5 estimators. This is the model. With the 10 estimators, this is the model. With the 20 estimators, this is the model. And with the 50 estimators, this is the model. Okay. So what is your observation? As the number of estimators are increasing, it will be able to capture this pattern of the data very well. Am I right?
But overfitting again.
Overfitting also some cases. And yeah, as I have told you, you have to decide where to stop. Yeah. Yes, that problem is there. You're right. Okay, but you see that as you increase the complexity, I mean number of estimators, it is allowing the model to learn the complex patterns in the data. That point we have to agree, isn't it? It is allowing the model to learn the complex patterns in the data. Okay. Now one more experiment that we can do is this. Will not change the complexity of the, I mean, will not change the number of estimators, but we will change the complexity of the underlying model. Okay, so I'm fixing the number of estimators to 10. This time I'm varying the maximum depth. It means I'm varying the complexity of the underlying model. So max depth 1 means less complex, max depth 5 means more complex, right? So you see that with the different depths, this is 10 estimators with max depth 1, 10 estimators with max depth 2, and so forth. You see that as you increase the complexity of the underlying model also, it will be able to capture the pattern. But here you see that whatever the problem that you have mentioned, overfitting problem, that is more in this case as compared to the previous one. Because the complex models means there is a higher chance of overfitting, right? Again, you can use the model, that regularization and everything for the underlying model, or any other pre-processing, pre-pruning, post-pruning techniques for the underlying model and reduce the overfit. Okay. So this is the demonstration. I haven't gone through the complete code line by line. So just to give you an idea, I've given, because I haven't discussed this gradient boosting technique. So I'm not explaining it line by line. But this is to give you an idea that how this addresses the problem. Okay, I hope to that extent you understood. Clear?
Yes, yes, sir.
Yes, sir. Yes, sir.
Yeah. So gradient boosting regressor, if you want, we'll continue. Otherwise, we'll start with the artificial neural network in tomorrow's session.
No, sir, we should not.
Little bit of gradient boost, we cover,
Gradient boosting.
then we
The
can.
gradient boost is very important, sir.
Okay, madam. We'll cover. Don't worry. So anyhow, I mean, I have agreed to take the extra classes, so I will take. So even if it is more than 30 hours, I will take.